Ha! The next piece of the puzzle in our process of building neoclassical model is cost minimization. Actually, now we need to discuss what companies, what entrepreneurs in our little economy are going to do, what are they doing? And look, I can tell you right away that what we're going to, the answer is cost minimization. But does it make sense to think about it like this? First, you might notice that in microeconomics, we were told that companies, entrepreneurs are seeking to maximize their profit. Well, now remember, how can we maximize the profit? Well, there are various different ways in which we can do this, but what about this particular economy? Look, first, we are considering what is happening in the economy in the long run. We have a situation in which companies can change all factors of production they use in a way they please. But of course, only the efficient way will guarantee that they will stay in the market and they will not be swept away by competition. Now, in long run, we do not have economic profits, right? So in order to minimize the loss in the long run, the best way to do is to get zero loss, and this can be accomplished by minimizing the cost. So actually, everything that the entrepreneurs in our economy need to do is to minimize the cost. Okay, so I just want to mention one thing. In this video, we will be using Lagrange multiplier. So if you don't remember how to use it, please check the link in the description. Watch the video. You'll be ready for anything we're going to come up with here associated with cost minimization. Okay, so first, let's consider how the cost of our company should be modeled. So let's just say CM denotes the cost for manufacturing, but of course, if we change this to food, we'll get the same thing. Because everything we're going to do here is very symmetrical and applies to both sectors. Now, look, what assumptions we've made about this economy? We said that there's a perfect competition in in markets for goods and markets for factors of production. So look, what does it mean? It means that if company produces manufacturers want to hire workers, it cannot control the wage at which those workers are hired. So if they want to hire LM workers, they will have to pay LM times the wage they need to pay to those workers. And this parameter is beyond the control of the company. And the same goes with rent for the capital they want to use in the production of manufacturers. Those two parameters are beyond the control. We assume there is perfect competition, so they can hire as many workers as they want without influencing the market price. But now, there is another feature of this cost function that I hope you can see. W, so wage, and R, rent, do not have a subscript N. Why? Because the companies from food industry and from manufacturing industry are actually competing for the same workers, and they are paying them the same wage because they get the workers on competitive markets. So in this case, we see that those parameters here are beyond the control of anybody in this economy. So we are taking them as given. So if I wanted to change this function to cost function of food industry, I would change this to F, but R and W would stay the same, right? Because they are for the whole economy. Okay, now, so we want to minimize this cost, but of course we need to produce it. For simplicity, of course we are going to still assume that we are going to produce 1 unit of merchandise. So, given the production function Km alpha m times Lm 1 minus alpha m, it needs to be equal to 1. Okay, and now, here we've got function that we want to minimize, here we've got our constraint. In these cases, we use Lagrange multiplier, and we denote the new function by capital Z, and it's going to be W times Lm plus R times Km plus, now we've got lambda, Lagrange multiplier, times 1 minus K alpha m times L m 1 minus alpha m. Okay, so what we're supposed to do now is to differentiate this function, right? With respect to 3 variables, we just need 2 actually, but let's do the whole thing the way we did it in mathematics. And we start with differentiating with respect to lambda. We get that this is 1 minus K alpha m and 1 minus alpha m equals to 0. Or, look, basically, if I get this is our requirement, right? So I can take this 1, put it on the other hand side of the equation, and as it should be, we simply, as one of the conditions, we have repetition of our constraint. But this is not of the key importance. Of the key importance are the next 2 derivatives. So we've got derivative of z with respect to Lm gives us W, and now minus lambda. Now we are differentiating this, so we get 1 minus alpha m up front, and then we just repeat what we've got, and with here we need to subtract 1 from the power negative alpha m. And of course we should equalize it with 0. So look, by the same token, to simplify everything, I can move this part to the other hand side of the equation. So I get that wage is equal to this entire expression. Finally, we calculate derivative with respect to capital. So we've got R minus lambda now times alpha m times k m to the power alpha m minus 1, because we're differentiating with respect to km, and the rest stays the same. And we equalize it with 0. And look, now we can do the same thing. I can move this part to the other hand side of the equation, and now I'm getting the expression for rent. So, what should we do now? Let's solve it a little bit. Okay, first thing we're going to do is that we're going to divide this equation by this equation. Okay, so we get the ratio of wage to rent, and let's do it step by step because clearly some things will cancel each other out. First, we've got 2 lambdas, which we will definitely cancel each other out. What else have we got? We've got, from here, 1 minus alpha minus m, 1 minus alpha m over alpha m. Here, and there's nothing we can change. Then we will have km to the power alpha m divided by km to the power alpha m minus 1. And then we will have Lm to the power negative alpha m divided by Lm1 minus alpha m. And here we definitely can also cancel some stuff out, because look, those two will cancel each other out. So here we have km to 0, which is 1. 1 divided by km to the power negative 1, which gives us km, right? Out of this we will just have km. Now, over here, those two will cancel each other out. So we've got 1 divided by ln. So instead of this, we will have 1 over ln. And finally, we get from this that wage to rent ratio is equal to 1 minus alpha m over alpha m times km over ln. Now, if I solve this for km lm, and look, this expression that you can see over here is actually showing us the optimal ratio of capital to labor at the point where we minimize the cost of production. So, in other words, if we want to minimize the cost of production, we should choose capital to labor ratio given by this. Now, if we knew the specific value, we could actually calculate the ratio, but we do not know it. But the more important thing is that we know how this ratio depends on intensity of the capital used in the production process, wage, and rent. And now, of course, some of those relationships are not that clear, so why not calculate comparative static derivatives that will tell us the exact effect? And then we'll try to figure out if those make sense or not. Okay, let me just denote it as K like this. And we differentiate first with intensity parameter, right? So, in this case, I can treat W, if I differentiate just with alpha m, I can treat W over R as a constant up front. Now, to the second part, I need to use the quotient rule. So at the bottom I get 1 minus alpha m squared. And now, with quotient rule, we've got derivative of the first one times the second one. Now, minus first one times derivative of the second one, which is negative 1. So we get plus alpha m, which gives us W over 1 minus alpha m squared r. And look, positive, positive, between 0 and 1, and taken to the power of 2, we can clearly be sure that this is positive. Okay, and so what do we learn from that? If, from the perspective of just production process, the bigger is the intensity of capital in the production process, of course, the bigger is going to be the ratio of capital to labor. So, if generally production process requires more capital, we can expect that the optimal ratio of capital to labor will be higher. It makes perfect sense. We can assume, along with the lines of the assumptions we've taken this far, that in case of merchandise, when we have capital-intensive technology, alpha m will be bigger and we can expect higher capital to labor ratio in comparison with food industry where technology is labor intensive. Okay, now let's move to the next derivative. Now let's see the relationship between price of capital and capital to labor ratio. Okay, look, I can rewrite this expression just to make things simpler as alpha m over 1 minus alpha m times w times r to the power negative 1. Right? You see, now it is trivial to differentiate it simply because the first part this part can be treated as a coefficient of a linear function. And now I will have minus 1 up front and r to the power negative 2 or r squared at the bottom. Okay, now positive, 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 positive with minus in front of negative. And again, does it make sense? Perfect. Look, if cost of capital is getting higher, we should expect that the capital to labor ratio is going to be getting lower. Simply because capital is becoming relatively more expensive. We talk about long run. In the long run, we can quite easily substitute capital with labor. So the higher the cost of rent, the higher the reward to capital, the lower will be the capital to labor ratio. Okay, now that we've dealt with this, the only thing left is wage. Now, this is the easiest derivative to calculate because all of this can be treated as a coefficient of wage. So we've got alpha m over 1 minus alpha m times w, which because we have all the positive components must be positive as well. And look, does this result make sense? Again, perfectly. If price of labor goes up, we expect that for companies it will be optimal to substitute more expensive labor with more capital, right? So if wage is going up and wage is beyond the control of the companies, then for the optimal strategy in this case is to substitute workers that become more expensive with capital. So again, we see that all these long-run solutions that we can figure out over here make a lot of sense, right? And this is not something anybody would like to argue. So let's get a little bit deeper with cost. Look, when we were discussing production first, from the perspective of production function, we've introduced isoplot for graphical purposes, and we can do the same in here. We're going to introduce now isocost or isocost line. So this is the line that shows all combinations of capital and labor associated with the same total cost. Okay, so now look, now we see that we can produce, we can spend the same amount of resources or of money on capital and labor, right? But we can buy them in different proportions. Now, how can we draw a line that that will show us all those combinations we can afford with a given amount of money? Well, as it turns out, it's way easier than in case of isoquant. Why? Look, because the cost function we had is W times Lm plus rent times Kn. Look, if I want to obtain this line, the best thing I can do is to solve this equation for Kn. And then, okay, let's do it in steps. So first, I'm moving everything away from Km, so I get that this is negative WLm plus Cm. Now all I need to do is to divide through by r, and I'm getting that Km is equal to negative W over r, Lm plus Cm over r. I hope you get some flashbacks from Introduction to Economic Analysis and what you've been doing there with Professor Chuck, and of course the same thing, microeconomics, budget constraint, right? So look, this is a linear function, right? Because those are variable things, the rest can be treated as constant. So if I want to draw my isocost line with labor here and capital here, what should I do? I should, when labor is 0, we've got Cm over r capital. So look, if I don't hire any labor and I spend all my money on capital, this is how much capital I can have at most. Then we see the coefficient. The coefficient is clearly negative. So we get a straight line that leads us somewhere around here, where we will have Cm, as you can guess, over W. This is how much labor we could buy if we would spend all our money just on labor. Okay, so this is the slope of isocost line. We can write it more formally, that slope of isocost, so d Km over d Lm is equal to negative W over r. Now, this should be somehow connected with this, right? We clearly see that those two ratios appear in optimal solution and in isocost line. So maybe there was one more place where we've seen something like that. Of course, this place was when we were talking about slope of isoquant. Right? We said that slope of isoquant, called marginal rate of technical substitution, tells you how much units of one factor of production you need to give up in order to get one additional unit of other factor of production. Is something that we found out previously, and we can write that d Km d Lm is equal to 1 over alpha m Km over Lm. Okay, so this is the result that we had in the previous video, right? And of course, I forgot the minus up front. I'm sorry, this is the result we obtained in the previous video. So this is the slope of isoquant. This is the slope of isocost. Now look, what will happen if I equalize them, right? If I'm gonna take this and equalize over here, right? What else can I do here? Well, definitely I can get rid out of minuses. And if I'm now gonna solve it for Km, Lm, what I'm getting is the condition that we've got from the Lagrange multiplier exercise. So what does it mean? It means that if we are at optimal point, this means that isoquant and isocost must have exactly the same slope. And again, this result should not come as a surprise to you. We've done things like that in different subjects, and we did it in subjects I didn't teach you. So, how can we present our answer in the graph? In a very classical way. Here we will have L, here we have K. And look, let's just say that we have one isoquant. We will call it M equals to 1 because we just want to produce one unit of manufacturers, right? And look, now, isocost, let's just say is the line that goes over here. But the question is this isocost, let's call it I1, a good option? Well, clearly not. First we have two solutions, but I can see that I could make the same amount of merchandise, 1 unit, at the lower cost. So what should I do? I should move this line until I will have this isocost line at a point where it is tangent to the isoquant. Right? And what can we say about this point? Well, we can say that here will be our optimal level of labor, which can be thought as a function of wage and rent. Why, I will explain a little bit later, but I hope we will derive it in detail. Then we have capital, that is also a function of wage and rent. We've got isocost, we've got isoquant, and now, if I'm going to take a line and draw it from the origin, then the angle of this line is going to give us Km over Lm, which is equal to alpha m over 1 minus alpha m multiplied by W over R. Okay, so look, now we've done the very same thing graphically. We will be referring to graphical explanations quite a lot for a very simple reason. Sometimes it's easier to show something on a graph than actually calculate it out. Okay, now before we finish and move on to another subject, I wanted to talk to you about one additional thing. And what I'm talking about is the connection between a capital intensity parameter and the share of the cost that is going to capital and by the same token labor in our companies. Okay, we remember that here we've got the is equal to alpha m over 1 minus over 1 minus alpha m times w over r. Look, I can take this and I can solve it to get ln w. Okay, so what should I do first? Well, I should multiply both sides by ln w and by ln multiplied by r. Okay, so we will get rkm is equal to alpha m over 1 minus alpha m L W ln. And now, if I multiply both sides by this and divide by this, I get the W ln is equal to alpha m is equal to, I'm sorry, 1 minus alpha m over alpha m times r times k. Okay, remember, this relationship is an equilibrium relationship. This is optimum relationship. This is what we get. In optimum. Now, I can substitute this relationship into something we know. We're going to need that to total cost, which is R times kW plus km W times L. Okay, so I got R times kW plus 1 minus alpha m over alpha m. Wait, did I skip a step? No. Good. Km R K M. Okay. So now look, if I'm going to put those two in common denominator, I need to multiply and divide this by alpha m. And what will I have here? Out of this I will have plus 1, which is RKM, RKM minus alpha m RKM. So, as you will see, I hope you can see, those two cancel each other out, and we are getting that this is all equal to RKM over alpha m. Okay. At this moment, this result should not tell us much, but if I'm going to combine this side with this, what am I going to get? Well, I'm getting that RK plus M plus W Lm is equal to RKM over alpha m. Okay, now I'm going to multiply both sides by alpha m and divide by total cost. What am I getting? That alpha m is equal to R km over R km plus W Lm. And what do we do? What do we have here? It turns out that in equilibrium, alpha, so the optimal, so alpha m, so capital intensity parameter, actually in equilibrium is equal to capital share of the cost. Because look, what do we have here? Rent times how many units of capital divided by total cost. So this is a percentage that tells you how much companies spend on capital. Okay, we will continue this subject and adding new elements to the model in the next video.